So now we have two position called tan A position. It's a tangent galvanometers based on that. So this is called tan A position. So tan A position means, if you remember the dipole, we used to solve two position of dipole. One was the end-on position, right? And second was the equatorial position, if you remember. So in every dipole problem, we have two positions, isn't it? Two standard position, I would say. Hello, guys. Yes or no? Do you remember?
Yes, sir.
The first position, the axial position, is called the tan A. And the second position, the the equatorial is called tan B position. So these are two famous position corresponding to the two standard answer. So tan A position, how to design? This is your compass. No, compass is anyway this circle. You draw two arms. Okay. Because you have only one dipole, you can put in any arm. The Earth magnetic field will be normal to the arm, or you can say perpendicular to the arm. So if this is the arm, the Earth magnetic field is going to be. So BH, I'm going to always keep vertical to solve my problem. And the dipole I'm going to bring here is this. So the center of this compass is at an axial position to this dipole. Yes or no? Tell me, guys. Do you understand? And because of this reason, the B external is something like this. Yes or no? Hello, hello, hello.
Yes, sir.
And now you have a compass. Not a good one, but in fact. Okay. And now, as usual, this will have its own axis. So the only thing is the B external is due to the dipole. And if I take this distance as R, and if it is really small, if the dipole moment is small m, or whatever m if you want to say. So generally in classical medicine, we represent capital M. And that is also a way to distinguish that it is from the classical medicine. We take the theta here again. So we know the forces will be here. How much? MBEXT. And this is?
Sir?
Yeah.
Sir, I got disconnected for a minute.
Okay, okay. Okay, so in the tan A position, see, if you remember the dipole, then every question of dipole we solve for two standard position, right? The axial and the equatorial, right?
Yes.
So in this topic called deflection magnetometer, which we use to find the dipole moment of the bar magnet, we have two position by the name tan A position. A means axial, you can say. So here A means axial and B is the bisector. So we call tan B position. Okay. So by these two names, and the purpose is same. I have to create two mutually perpendicular magnetic field in which one is by default the Earth's magnetic field. Is this clear, guys?
Yes, sir.
Yes, sir.
M B E X T. Okay, what you are supposed to remember to solve question? These diagrams. If you don't remember, you can't solve any question. So the standard answer is simple. B E X T is BH tan theta, or tan theta is that, it's same thing. At equilibrium, we can write like this, yes or no? Tell me, guys. Hello.
Yes, sir.
And B external, we know the answer. Can we say B external is mu naught by 4 pi 2m by r cube, because we take r to be very large compared to this. So if you're looking for m, you can get m. That's simple. 2 2 So generally in examination, you're supposed to write this answer. And once you have this answer, you can do whatever they ask. So they may give you something, they may ask you something. So this is called the tan A position. Axial means A, okay? A for axial. What is the tan B position? Tan B position. Tan for tangent, B for bisector. So it is called the equatorial position. You can just to remember, you can say B for bisector. But see, no matter whether you take the tan A or tan B position, the two fields must be mutually perpendicular, isn't it? Which two fields? The two fields, the BEXT and the BH, must be mutually perpendicular. So to design the tan B position, the rule is this. Bring the arm at the bottom like this. Then your job is done. So if this is the North Pole, if this is the South Pole, at any axis, equatorial position, the direction of B will be opposite to the dipole moment, if you remember. Isn't it?
Yes, sir.
And now my diagram is intact. The way it was, it is similar. So my BH is always like this. So you have to also learn that how to draw the diagram to get the answer. So very soon we are going to see the JEE-Mains problem so that we can get some confidence. Okay. So, okay, no, not this much. Just one is sufficient. So this is my BH. And then again, I have to draw the same typical compass diagram. Let me change the color. So orange will go with which color? Okay, let's select green. And again, it's a similar thing. So can we always, kind of remember this is B external is BH tan theta. Now the thing that will change is the formula. Which is the formula? Mu naught by 4 pi. It is m by r cube, right? Earlier it was 2m by r cube, not is m by r cube. Do you remember this?
Yes.
For equatorial position, the answer is half, right? Okay.
Yeah.
So anyway, you have to just remember this formula and you're done. So this was the deflection magnetometer. Why we use? So we use it for to find the unknown dipole moment of a bar magnet, or if you know the dipole moment, you can find the BH. Okay, so if you know something, you can find something else. That's the whole purpose of any mathematical equation. So that is the tan A, tan B position. This is the deflection magnetometer, which is based on the tangent law of perpendicular fields. So is this clear to all of you guys?
Yes, sir.
All right. Sorry. The next device is called oscillation magnetometers. Okay. So these are very standard answer. Oscillation magnetometer. So what is oscillation magnetometer? What is the purpose of using this? So we are going to oscillate dipoles under the action of BH, the horizontal component of earth field. So we are going to suspend bar magnet from vertical string, and it is suspended in such a way that the bar magnet remains horizontal. It is not supposed to move vertically. So dip is not possible. We make sure that the device is designed in that way. So generally it is kept on the ground in a box in an airtight container. So you can draw or think a diagram like this. So it is airtight container. You make a hole, a wire will go inside, and this is kind of fixed, and a bar magnet is attached at the bottom. It is touching the floor, so anyway you can understand it cannot move, right? But because it's a frictionless surface and there is no air resistance in this this glass case, so the BH can easily rotate, right? And the BH we know is parallel to the earth surface. So as if it is not aligned with BH, it will oscillate. Okay, so it will have some time period. So anyway, what is the purpose of using this oscillation magnetometer? The answer is it is used to compare dipole moment of two. If you know the purpose, you can easily solve. Bar magnet. So the purpose is to, we find the time period, and then from the time period we can compare the. So what you need to remember for this particular topic, so you should remember the formula. Time period of a bar magnet oscillating under the magnetic field is 2 pi under root moment of inertia upon mb, right? The only difference is replace b by bh. Is this clear?
Yes, sir.
Typical oscillation of a dipole. If you know the dipole oscillation, so we have to compare two dipoles, right? So what we do is you can take two bar magnet and you tie to each other, like you kind of clamp it. So how you clamp it, that you know. So if you clamp it, the north, the south, the north south. You can also clamp in two other way, right? Generally, you're not supposed to calculate the moment of inertia. They will give you the moment of inertia of each dipole, I mean, each bar magnet. And this is the suspension. Because the dipole moment is in the same direction. So the net dipole moment of the system is how much?
M1 plus M2.
And if I call the moment of inertia I1, I2, so I total is how much? So it is again a scalar, we can just add, right? Okay. The other way to suspend the same dipoles by reversing the polarity. And once you reverse it, it is south, it is north. So moment of inertia will change or remain same, tell me. The I total will remain same or change? Same. So I total is not going to get affected. It is still I1 plus I2, it is scalar. But what about the M system?
It will be the difference.
Yeah, so it will be the difference. So can we say mod of M1 minus M2? I don't know which one is bigger, right? So I can write either M1 minus M2 or vice versa. So the time period of the first will be different from the time period of second because of the factor is changing, the M is changing, right? But the moment of inertia is not changing, BH is not changing. But anyway, what is T1 you can write in general? And T2 can write as? So is the formula clear to all of you?
Yes.
Yes.
For a typical bar magnet, you should know the answer for the moment of inertia as well. Let me show you what you are supposed to remember. If a bar magnet is oscillating in this fashion, let's say the length is A, width is B, and the depth is H. If the oscillation is happening about this axis, then which dimension will matter to us? A, B, H, which will matter?
A.
A and B both, right?
A, B, A, B.
It's a rectangle. H will not
Yes.
matter because H is the depth. So with the moment of inertia, if you remember, it is mass m by 12 A square plus B square. Basically, this is the perpendicular axis term, right? Which you don't remember, right?
Yes, sir.
Again. About this axis, we know the answer. MB square by 12. This axis M A square by 12, and therefore the answer is the sum of the two. So one should remember this typical answer of moment of inertia for the cuboidal shape bar magnet. I have also given a formula for the cylindrical, right? So these two formulas are, I mean, one should be aware of. I don't know whether they will ask or not, but they may ask, and therefore I expect that everyone should remember this answer. Okay. So The T1 and T2 we have, you can see it is inversely proportional to the M net. So what is the ratio of the two? So T1 by T2 is how much?
M1 minus M2 under root of M1 minus M2 upon M1.
So you may square both sides. So T1 square by T2 square equals to, okay, let's take M1 as positive, bigger, M1 minus M2. To solve, I have to take something as positive. And from here, can we take the ratio of the two? I mean, you can rearrange your component or dividendo the way you want. Okay. So if I add one both side, what I'll get? Okay. Anyway, you simply multiply and get the answer. M1 T1 square, M2 T1 square, M1 T2 square minus M2 T2 square. Rearrange the M1 separately. So M1, it's good to do this way. So I'll take this side. So M1 T2 square minus T1 square is equals to M2. So M1 by M2 is how much? The difference, M1 minus, yeah, the sum upon difference. Take a mod if you are if you want positive answer anyway. So this will give you the relation of the comparison of the two dipole moment, and the benefit is if you know the answer of one, you can find the other. Understood? And time period is measurable quantity, right? Is this clear, guys? Tell me.
Yes.
Okay. Okay, next what you can find is, see, rest of the question will be similar to the electrostatics, but these are the something extra. The last topic left is the magnetic properties of material, right? That is the last topic. So shall I do the question first of this topic, or then start this topic, or shall I finish this part? Tell me.
So when I said then we'll do all the questions together.
So I must finish this part first. Are you saying this?
Yeah.
Okay. So magnetic properties of material. So what is the magnetic properties of material? What do you mean by this? Or what is magnetic material? So every material is made of what? Atoms, isn't it? So even if I take a smallest volume of object, let's say if I take 1 millimeter cube, I have explained this. In a cube of side length 1 millimeter, how many atoms can reside? Exactly, draw a cube of 1 millimeter side. So how many atoms can reside in that tiny volume? Any guess?
Sir, each atom has a volume of 10 power minus.
So it is roughly 10 power 20 atoms, which is tremendous, isn't it?
Yes.
So if you
Sir,
have yeah, tell me.
sir, each atom's like approx volume.
So you can take 1 angstrom as a dimension. So each atom will have the volume roughly 10 power minus 30.
Okay, sir.
So 10 power minus 9 upon 10 power upon 30 is 10 power 21, right?
Yes, sir.
So that's why it is roughly 10 to the power 20 atoms. Now, 10 power 28 is a large number. Okay. So if I take that 1 millimeter cube and if I zoom out, what you will see that every atom will have its own dipole moment. So if atom is assumed to be a circulating electron, so it will have some dipole moment. In a single electron system, then can you say that every atom must have some dipole moment, isn't it? But as the number of electrons will grow, it is quite possible that these electrons can cancel their because of the direction of rotation, they may cancel the net dipole moment of each atom. Quite possible, isn't it? So whenever we have the unpaired electrons in an atom, when you write the electronic configuration, then the chance of cancellation will go away, and therefore some sort of magnetic property can be found. Now that is the property of atom. Now we have 1 millimeter cube as an elementary volume. Let's say this is the small volume. If you zoom out, you can see a large cluster of atoms. And this diagram I'm going to draw is the cluster of atoms in 1 millimeter cube. So I can divide that 1 millimeter cube into infinite clusters. So what is cluster? So cluster is a region in which the dipole moments of atoms are aligned in one direction. And this cluster we called by the word domain. So if I think of this as a domain, then the dipole moment of every atom in this particular region will have one particular direction. And what I have drawn is the elementary volume. Every elementary volume will have infinite cluster, not one. So this is just symbolic to you. Okay. Then you can get some other cluster. And in this other cluster, the atoms may be aligned in a random fashion. So the question is, what keeps them random? So the answer is, it is the thermal energy which keeps them random. Then you may design some other cluster. Other cluster. So I have taken some random. And this cluster may have something like this. So every cluster will have some random direction. Can you see this cluster now? Oh, you can't see, right? Oh, I've done this intentionally. You can see this is cluster. And this cluster is actually, can you see the cluster now? It is gone. It's like a dot, right?
Yeah.
Yes.
In that dot, I have drawn those things. Do you remember? And I have drawn few numbers. It is actually infinite in that dot. Oh, come back to the reality. So this is the cluster or the domain. So this is called the domain theory of magnetism. So domain theory, it was in my time, it was in class 8 syllabus. I don't know why they removed. So every magnetic material will have dipole moment actually divided into clusters or domains one domain represents one particular direction. This is kind of model. Okay, don't take it exactly. And in that tiny volume, because we have the randomness of the cluster, therefore, the total vector sum in many cases is found to be 0. Or you can say the total dipole moment is found to be 0. So if the total dipole moment is 0, then it will not exhibit the magnetic characteristic in general. But it is still magnetic material because the dipole moment is present in the volume. If there is no dipole moment present in elementary cluster, then definitely it could be non-magnetic. In such case, we have to induce the dipole moment the way we have done in electrostatics. So what happens when such material is kept in the magnetic field? What will happen? So let's say you bring this entire substance into some external field. So every dipole will experience torque if it is not aligned, isn't it?
Yes.
If it is not aligned, then all are going to experience torque. Now this torque will definitely try to align, but there is some other constant called, what do we call? The lattice constraint or lattice spacing. Because lattice will not let you rotate freely, isn't it? You are part of lattice, you're not part of air or gas. So these are basically materials, solid materials. So they have some sort of structure, crystalline structure. So what happens? That they fail to rotate as per their will. And if you try to make a very strong field, then rotation will occur, but at the expense of some internal deformation, which may lead to some heating effect as well. So when you do a, a quicker, magnetization and demagnetization process in a material where the lattice spacing is really poor or where the words are not present, then this rotation creates enough heat to act as a heater. Okay, so we can also use that eddy current effect. We can actually align these domains and we can create a lot of heat. Okay, so the magnetization and demagnetization may lead to the heating effect, and you can boil something using this effect of magnetization or demagnetization. So anyway, the domain theory is very simple. When we have a any material, then the dipoles are randomly kind of oriented, and these dipole moments are divided into tiny cluster. One cluster is defined by one direction of dipole moment, but the net vector sum is 0 in most of the cases. If it is non-zero, then of course we will have net dipole moment vector, and that net dipole moment vector will give you a very weak attractive power. Okay, so the normal lodestones are example of that effect. In the normal lodestone, which is having the weak attractive power, they're found in nature because their dipole moments are not getting cancelled. Okay, but once you put into field, the dipole against the field will start shrinking in size, and the dipole which is close to the direction of, or you can say, which is kind of acute, making acute angle with the field lines, will grow in size. Okay, so there is a you can say shrinking and expansion of domains. So the favorable domains will grow and the unfavorable will shrink, and that you can say asymmetry that will develop by the application of external field will lead to creation of a net dipole moment, and so the material will start exhibiting the magnetic character which you generally know. Understood? Hello, is this clear?
Yes.
So we have to define something called intensity of magnetization vector or I vector. Intensity of magnetization magnetization vector or I vector. What is I vector? So in the presence of applied field, what will happen? The volume of the material will have net dipole moment. Earlier it was zero because of the randomness, right? Because of the thermal randomness, the vector were canceling each other, right? But once you bring into some external field, what happens? The cancellation will go away. It will have some net value. Okay. So that net dipole moment induced per unit volume is called intensity of magnetization vector, or simply intensity of magnetization, that how good the medium is to get magnetized once I create some field. Okay. Or how much net dipole moment I am able to induce per unit volume of the material. So more I can do, I am a good magnetic material. Okay. A poor will try to create lesser value. So intensity of magnetization is the ability to get magnetized. Okay. Under the application of external field. Okay. So we called intensity of magnetization. The definition is simple. It is defined as net magnetic dipole moment induced per unit volume. Yes, we can say. So we can add I equals to summation of all mi upon v. We can simply say capital M by v. V is scalar, volume is scalar. So that is the definition of intensity of magnetization, or you can say it actually gives you the sense of the ability to get magnetized when you are kept in the external field. So you may have the randomness, but once you come into a field, then how quickly you can align your dipoles and create this net dipole moment. So that's called the intensity. Okay. So I gives the measurement of ability to get magnetized once brought in external magnetic field. I hope this is clear to all of you guys. Hello, hello, hello.
Yes, sir.
So we can easily find the intensity of magnetization for what? For a bar magnet. You can do it for the solenoid also. So for a bar magnet, if I draw a bar magnet this way, so I will not go give you A, B, C. I'll give you the cross-section area. So let's say this is the area A, the length L, And then if I call the North Pole M, South M, so what is the dipole moment of this bar magnet? ML, correct?
Yeah.
So the intensity of magnetism in scalar form we can write as M by AL. So M is how much? ML. So basically you can see it is pole strength per unit area, right? So intensity of magnetization of a bar magnet is what? Pole strength per unit area of cross section. I hope this is clear to all of you. If you do it for solenoid, of course, I by default I will take infinite solenoid. So if I is the current, what is the dipole moment here? NIA, correct? And capital N we can replace by what?
N by L.
Small and into it.
Sorry, small n.
Very good. So the intensity of magnetism by definition is dipole moment per unit volume, right? So NILA and volume is AL, isn't it? You can see the N into I itself is the intensity of magnetization. These conversion or comparison kind of question may come in the examination. I hope this is clear. Hello, hello.
Yes, sir.
Okay, so the ability depends on what? NI. So that's logical. If we have more number of turns per unit length, it will have more ability, isn't it, for a given current? So as we increase the number of turns per unit length, the intensity of magnetization will increase, isn't it?
Yes,
Hello,
sir.
hello. Any doubt in this? Tell me, guys.
No, sir.
So now we have to find some more relation. So imagine if you have a solenoid which creates its own field, right? And then what happens? Let me do once again. Okay. Okay. So if it is solenoid, what is the field inside the solenoid if the current is I? So we know the B inside the solenoid is how much? Mu naught Ni. So if it is nothing, if air is inside, air. So if you remember that in capacitor, we have the parallel plate capacitor, then you can insert some dielectric. So it becomes paper capacitor, mica capacitor, or some liquid capacitor. Similarly, if we have a solenoid, nothing is there, it's an air solenoid. But you may insert something having the magnetic properties, having some domain, already inbuilt domain. And what will happen the moment you put inside, the domain will start aligning themselves as per the field which is already present. And as a result, the net field inside the solenoid will be more than applied or less than applied or equals to applied. What will happen? Tell me what will happen.
Sir, more than applied.
Yeah. So the thing is, the field which you have applied and the field which is coming because of the, because of the alignment process, the resultant field will actually having the sum of the two. It is the combination of the two. Okay. And therefore, we have to separate the applied field from the resultant field. And to separate these two, what you apply and what you get as a result of the medium inserted, we have to define one auxiliary field. So we have something called auxiliary. What is spelling? AUX. Auxi. Tell me guys, what is spelling?
AUXILLARY.
Okay. Tell me, Hasika, AUXI?
LLARY, sir.
LL.
Sir, LIAR. Auxiliary.
Auxiliary. I mean, I don't know. Oh, I'll search. See, something so simple, we get confused. That's the reality.
Sir,
Yeah, it's
yes, sir. There's an
yeah.
extra I.
Yeah, AUXLIARY, auxiliary. Yeah. If you can speak women, okay, that you can get. Anyway, so what happened that whenever you're applying field, you're getting more than that. Okay. So the magnetic field is what you get in the region will have contribution from the induction process also and the applied also. So we would like to define something which do not, get affected by the induction. So something which is free from the induction process, and that field we called the magnetic intensity. So we define something auxiliary field called magnetic intensity. And this has been inspired from the intensity of magnetization. So this magnetic intensity, which we represent by the capital H, it always takes care of the field which you have applied. It will always try to eliminate the induction part, the induced part. And therefore, the definition of this H is unique. So in any space, in any medium, the H vector we define as the resultant B. B here representing the net value of B, which we don't know. Okay. So the resultant B upon mu naught, because it is to do with the intensity of magnetization. So to make it dimensionally correct, if you know B equals to mu naught Ni or mu Ni for medium, you can replace this B equals to this and B equals to mu Ni, where mu is medium permeability. How to remember is, you can add this. This is the part you have to remember. So H is equals to B upon mu naught, which is the net dipole moment in the present in that volume, minus what will happen due to the induction effect. So we write minus I. So that is how we define the H value. So what is B representing? The resultant magnetic field induction, which will have contribution from the applied and induction both. Okay. So here B represents magnetic field induction due to applied and induced both. Now look at this formula. If there is no medium, what will the answer? So H is B by mu naught minus I. That is always true. If there is no magnetic medium, then I will be how much, guys? If there is no medium, then do we have the induction? Tell me.
No, sir.
No.
So if there is no if there is no medium, then the I will be 0, isn't it? And in such case, the H we can write as directly B naught by mu naught. In scalar value, what we can write? Okay, this is the formula, but you can add here directly. So in scalar form, the H is basically B naught by mu naught in the absence of medium. And if you remember for a solenoid, what is B naught? Mu naught Ni. So basically Ni, and Ni was the equivalent intensity of magnetization, right? Isn't it? Now this I is the equivalent, like which we try to compare with. It is not the induced part, it is the comparison part. So for any solenoid, okay, I will remove this part. So for air solenoid, what is H, guys? For air solenoid, H is always Ni. Understood?
Yes.
Okay. In fact, this is always fixed value, because the medium which you will insert will have its own contribution, and that contribution we have to ignore if we are trying to find the H. H means something which is not getting any contribution. It is due to the applied field only. Okay. So H is always calculated by the applied field only. We always try to remove the induction part while we define the magnetic field intensity. What have I written? Magnetic field intensity. So in scalar form, you can write like this. Okay. And these are just few formula which you need to remember. I'll show you the question in which I'll tell you how to apply it. The next concept which you need to know is called magnetic susceptibility. Susceptibility. And the symbol is, how to say? Chi. Okay, you can pronounce as chi. Hello, hello. So how we define this susceptibility? So it is defined as intensity of magnetization, or you can say dipole moment induced per unit volume per unit magnetic field intensity, or per unit applied field intensity wise, not field wise. So it is defined as intensity of magnetization per unit magnetic field intensity in a medium, in a magnetic medium. So if you have any magnetic medium, and if you are if it is under the effect of some applied field, the intensity part, magnetic field intensity, it will have some intensity, and it's a dimensionless quantity, because the intensity of magnetization and the magnetic field intensity both are same, right? If you remember, I was also Ni, we compared. So dimensionally I and H are same. So X is what? Dimensionless. So you can always at I mean, you can at a scalar form, you can at I upon capital H, or basically you can say the induction is proportional to H, and therefore when you put equal, you write susceptibility. So the way you want to define, you can define. So I is basically susceptibility into magnetic field intensity, what you apply. Okay. And susceptibility is like sensitivity, like how quickly you can do this magnetization process within your medium, within yourself. So these are the equation which you are supposed to remember. I equals to susceptibility into H, and H equals to, so this is the answer, of course. Let's not put here. So in this topic, in terms of formula, what you are supposed to remember, the answer is very simple. You are supposed to remember only two formula. The H equals to, write B upon mu naught minus I. Okay, B upon mu naught means B net upon mu naught. And the second formula is I equals to, and there is no other formula you are supposed to remember. If you remember only these two formula, you can solve any numerical from magnetic properties of material. Can we substitute and get some better answer? Let's replace I. So from 1 and 2, what you can say? H equals to B by mu naught minus. Now rearrange. So what is B value? B is mu naught 1 plus susceptibility into H. And what is B naught value? So B naught we write as mu naught into H, if you remember. So B naught means in vacuum. This is in medium. So we define something called, okay, the relative value. So mu naught into 1 plus susceptibility we call mu value. The entire term is called mu. This entire term. And this mu is called permeability of medium. So again, this is a new formula for you. And mu upon mu naught is called relative permeability. and that is in accordance with the electrostatic as well. There we have also defined the relative permittivity by dividing epsilon by epsilon naught, right? So you have the formula which you want. So you can say this is also one formula. This is also one formula. So in general, B is the way of writing B is mu H. This is always true. And you can also write as mu naught mu R into H. Or you can write mu naught into 1 plus susceptibility into H. Now the choice is yours. All formulas are in front of this page. And you have to deal with only these formulas. Is this clear?
Yes.
Okay. So with these formula, you can solve any question as you wish. Okay. Now I will talk about the types of magnetic substance. So you know in chemistry, but still I repeat it. Just a moment. Types of magnetic substance. So how many types of magnetic substance we have? Tell me, guys.
3 types.
There are 3 types. I mean, if you know chemistry, it's you know. The first is called paramagnetic. Second is and third is so what is paramagnetic? Tell me, guys.
Substance which are attracted
By
by a magnetic field.
yeah, so it is called weakly attracted.
Yeah, weakly attracted.
So weakly attracted. What is diamagnetic?
Weakly repelled.
Weakly repelled. What is ferromantic? So very, very strongly attracted. So in case of, see, I'll tell you something interesting. Diamagnetism is part of all magnetism. So there's nothing, I mean, there's no substance which cannot show diamagnetism because it is the induction process. So in every atom, you can always induce diamagnetism. We call by the name para or ferro depending on the dominant feature. So dia is something which is part of every feature. It means in every medium, you can have some induction. Okay. So some dipoles which are collapsing, I mean, some dipole moment which are collapsing under the field, they can separate out. Imagine there are 2 parallel loop and the current direction is exactly opposite. So it will create a dipole moment like this and it will create a dipole moment like this. And if it is almost coinciding loop, the net dipole moment will be 0, isn't it? Now, what will happen if I create a external field, H field? The one which is parallel will move in which direction? The parallel will move in the direction of H. Okay. And this the weaker will, I mean, you can see the opposite will move in the direction opposite of H, which means if PM and H are parallel, then PM will drive itself towards the stronger value of H and vice versa. I'm saying they will kind of separate. It is like if we have the plus and minus charge, and if we apply the electric field, the plus will go in the direction of field, right? And minus against. So although plus and minus was coinciding, but as a result of the field, what will happen? They will separate and will become dipole, right? This is called the induced dipole. It was not earlier present, but now we have induced. Understood? Similar to this concept in magnetism, when the two loops are almost coinciding with opposite current, they cancel the dipole moment, but once they are coming into field, they kind of separate and fail to cancel the PM values of each other. And so a net dipole moment is induced, and such dipole moment we call diamagnetism. Is this clear what I'm saying? So dia is, kind of coming into picture from zero. So dia means it was not there and you created. But para and ferro is different. What is para and ferro? It is there, but you realign. So what you're doing is you're trying to create a bigger domain in the direction of H, and you're shrinking the domain which is against the H. Okay. And in para, it is happening at a small scale, but in ferro, it is happening drastically. So are you getting the idea of para and ferro and dia? What is happening? In dia, we don't have any domain. It's a no domain. But in para and ferro, domains are there. So dia is like, even though there is no domain, you create a domain. You kind of disturb the, the neutrality of dipoles, and you create some dipole moment out of nowhere. So when you do so, it is called diamagnetism. So diamagnetism is about creation from nothing. But para and ferro is kind of alignment of the existing dipole. Okay. Or you can say realignment of the domains. Is this clear, guys, what I'm saying? Hello.
Yes, sir.
So what happens when we have a paramagnetic substance in a material, in external field? The dipoles will, you can say, partially align and will add to some magnetism, and some dipole will also be created because of, because from nowhere actually, because of the applied field. So a para is always accompanied by dia, but the dominant feature is para, and therefore the net, that's why I see what is happening. The para is trying to create a bigger value, the dia is trying to cancel the value, the net is always a weaker field. So in the para, the diamagnetic effect is actually kind of present significantly. Therefore, the the net attractive power is very weak. So in para, dia is there. In ferro, the alignment is to such a great extent of the existing domains that all other effects get cancelled out or can suppressed. So when someone will ask you that is diamagnetism property of, you can say, they'll ask you a question that is diamagnetism only for non-magnetic substance, or it is also for the magnetic substance? The answer is it is for all substance, whether it is magnetic or non-magnetic. It is just like its presence is not felt every time. Okay. So para, dia, and ferro will have this feature. The domain alignment is powerful in ferromagnetic. In para, it is weakly attractive, which means it will have some partial domain alignment, and then that induced dipole moment in the opposite sense, which will have some cancellation. So if we have a diamagnetic material, then it will try to go away from the field. Okay. So you may get a question like this. Imagine in a glass tube, which is a very common question. And it is filled with some paramagnetic liquid. Maybe the liquid oxygen, right? You know, liquid oxygen is paramagnetic.
Yes, sir.
So imagine this glass is filled with liquid oxygen. And what we do is we also put a North Pole and South Pole. So in case of, I mean, if there is no magnetic present, if I put some liquid, it will have equal level on both sides, isn't it? In a glass tube, if you put some liquid, it will have same level on both sides. This is what we expect, yes or no?
Yes.
But if you put a, you know, if you put a magnet, and if the liquid is paramagnetic, what will happen? Because
It
they
will
are
be-
weakly attracted, so more liquid will try to come close to magnet, which means the liquid level you will see more on this side and lesser on this side. Do you realize this? What is happening?
Yes.
So because of the paramagnetic property, it will try to occupy more. More of the liquid will try to go close to the magnetic poles. So I have put some pole. This is the diagram. But if we have some diamagnetic liquid, what will happen? The reverse will happen. It will avoid the field. So it will try to go away from the field. Understood what I'm saying?
Yes, sir.
So you can draw the same diagram. So you may get a question like this in examination. They will draw the diagram and will ask you identify the nature of liquid. And it's a simple question. It's fairly easy to identify. So even if you know a slightest property of paramagnetism, you can answer the question without any ambiguity. Okay. So if I put a north and south pole here, and if we have a liquid inside, then the liquid will try to go away, and therefore the level will be more on the which side? Other side, right? Is this clear?
Yes, sir.
Okay, for Pharaoh, I will not show. Okay, you know what will happen. So, okay, the maximum will be tried to be there. Anyway, what else we need to remember? The susceptibility. For a diamagnetic substance, the susceptibility is positive or negative? So the susceptibility for the para is between 0 and 1. It is weak, so it is positive but small. But for diamagnetic, the susceptibility is negative itself because it is kind of cancelling the field. So the susceptibility for diamagnetic is from -1 to 0. It is negative but a fraction. So what about the susceptibility of the ferromagnetic? It is much bigger than 1. It is like thousands. And therefore, if you remember the formula for relative permeability, it is 1 plus x, right? So it is in case of ferromagnetic substance, we can write a roughly x only. That's okay. The 1 plus 1000 is 1000. Okay, you know what I'm saying. But in case of dia and para, okay, I'll put this heading again. Para magnetic so the mu r will be how much? 1 plus x, which is now it is more than 1, right? So if x is from 0 to 1, then mu r will be from where to where? 1 to 2. Hello, hello.
Yes.
Yes, sir.
And diametric mu will be. So it is going to be from where to where?
0 to 1.
It is positive, but 1. Yeah, 0 to 1. Yeah, this I have already discussed. So this is what you are supposed to remember. Now we have to study something called the Curie's law. You know what is Curie's law? They are just simple formula.
So there are two other types of substances also. Ferry and antiferro.
I mean, of course, it is there, but in our syllabus, we have to study only 3 types.
Oh, okay.
Yeah.
Because
So what
they
is
were there in
Curie's law?
chemistry, but like our teacher
Ah.
told us that you'll study in more detail in physics, so I'm not teaching right now.
Okay. Okay, yeah. Anyway, so you can read about it. It's just Google it, we'll get to know.
Okay.
So now what is Curie's law? So first of all, you need to remember that a Curie law is only for the paramagnetic substance. You can say material, paramagnetic material. So what Curie law says that it's a very common sense. As you start heating any paramagnetic substance, the thermal agitation will lead to the more randomness. And as the randomness will happen, the domain will become again completely random. And that will lead to the loss of magnetism, isn't it? So it is common sense that the susceptibility is going to be inversely proportional to temperature, isn't it?
Yes, sir.
Okay. So the X will be C by T. Now the same thing you can say that if we have a ferromagnetic substance, then if we start heating continuously, what will happen? At some instant, the ferro will become what?
Para, sir.
It will become para. And once it will become para, it will start following the Curie's law again. So if a ferromagnetic substance is heated, then at one particular temperature, it will at one particular temperature called, what we call the temperature? Curie temperature. And we represent by symbol TC. It becomes paramagnetic. And then the susceptibility, it will follow the Curie laws. But the way of writing will be what? C by T minus TC. Like beyond the TC, you have to write the Curie law, not before TC, right? Understood. Hello, hello.
Yes, sir.
So once you have become the paramagnetic, then you will start follow the Curie law. So for paramagnetic, if you know a substance is paramagnetic, then you can write the answer this way. But if you are trying to convert a ferro into para, then you have to write this way. Okay, and the TC is called Curie point or Curie temperature. So these are some basic fundamentals, just try to remember. So we call Curie point or Curie temperature. Okay. Now comes the last concept. So this is called the magnetic hysteresis curve. So what is magnetic hysteresis curve? The word hysteresis means to lag behind. So the hysteresis means to lag behind. Okay. So this graph is all about H versus I. Oh, my bad. The I is the induction, H is the application, right? So H versus I we call this graph. So what we do is you take some ferromagnet and put inside the solenoid. So if you take a solenoid, and take some object, some mass, some substance. You can take generally iron, soft iron, or steel. Okay, steel doesn't mean stainless steel. Steel is an alloy of iron in which we only add carbon, right? But in stainless steel we add chromium, maybe cobalt, something else, right? So if we have a solenoid and if you insert some magnetic material, and if it is ferromagnetic substance, what will happen? As a result of applied field, the alignment will also start happening as per the field direction, isn't it? So we are going to create a field like this. And for solenoid, what is the H value? If you remember, H is how much? For solenoid, always we remember H equals to
Ni.
Ni. So as you increase the current, what will happen? The H will increase, right? And as you increase the H, what will happen? The domains will try to align themselves, right? So I will grow. And because susceptibility of the ferromagnetic substance is very high, so I will grow. But is it possible to keep on growing the I, or will it saturate somewhere? So there is a limit, no? If every domain is already aligned, can we further align it further by increasing more H?
No.
No, sir.
So that is common sense. And therefore, if you plot the graph, as H will grow, the I will grow. But after some time, it will stop growing. It will kind of saturate. Let me do better. This is not a better one. So it will grow first and it will saturate. Like this. This is the first process. It will become almost flat. So here, if you draw the tangent, you can see it is exactly parallel to this line. So this is the saturation value. It is IS. You cannot go beyond this. Now it has saturated. Now, once the alignment is done towards left, because the the field was left, so it is going to align left. If I start reducing the B, if the field is still start becoming weaker, the alignment will decrease or remain same. If H goes back, then what will happen? See, you are aligning it, but under the thermal, you can say energy, it will try to always vibrate and go back to the randomness, right? So thermal energy is always the creator of the randomness. So it is like you're forcefully holding it there. And as you decrease the H further, it will start decreasing as well. But all domains cannot go back to complete randomness unless temperature is not very high. Because the crystalline structure of the substance will not let all domains to go back without any force. So I will decrease, but it will not go back to 0. And therefore, if you plot a graph for decreasing part, you will see the graph will go something like this. Even I have made the H 0, I can clearly see nothing is happening. And I have left with something I. So this is called IR. You know what is R means? Retention. So there is a word retentivity. So this much you still retain, even there is no field. Even if you remove the field, you are going to retain somehow that value. So to make the retention go back to 0, if you want to, make this medium again go back to the initial value, what you're supposed to do now?
Reverse the field.
Exactly. You have to reverse the field. And you have to force it to make it 0. So what you do is you reverse the field and you try to make this somehow 0 somewhere. So this is the value of H at which it will become 0, and we represent by C. And you know what C represents? You coerce to make it 0. You force. So it's called coercivity. What do we call? Coercivity. Do you realize this? Hello, hello.
Yes, sir.
Now, once this is 0, like once we have achieved the coercivity, now it is the back to 0. The all induction has been lost. But if I continue increasing the field in the left direction, the alignment will again start happening, but in which direction? In the opposite direction. Therefore, you start creating alignment, but again it will become how much? It will become saturated, because you cannot go beyond this, right? Saturation has occurred. Can we go beyond this? No.
No, sir.
No.
And then you do the reverse process. You try to decrease the I, and then again, what you can see that it is always becoming 0 behind the origin, right? Behind where you started. That's why it's called hysteresis. So where it is supposed to 0, it is happening behind it. It is lagging behind. So again, you can repeat the process. And this time again, you won't get 0 here. You will do the reverse process. You will change the direction of field to make it again 0. Okay, it should be symmetrical, but anyway. And then again, it will go back to the same saturation. So this you can see there's a leaf shape object. We have created a leaf shape object. Okay. So this leaf shape object actually represents energy density. So how much energy, the bigger the area means, that much energy is lost per unit volume in one cycle of magnetization and demagnetization. Okay, so from where you started, so you magnetize to saturation, then you go back to zero, you magnetize to the other direction, you go back to zero, and then again you magnetize to the same value. The one complete cycle will create or will dissipate the energy, and the area under the graph is the representation of that energy loss per unit volume, or you can say energy loss density. So this area is having some meaning, and you're supposed to know its meaning. So do you realize what I'm saying? This area, what is the meaning of area? Okay. So is retentivity good or bad?
Depends on our use.
Exactly, it depends on the application. So let's say you are in a dockyard. In dockyard, you have seen containers, right? At least in movies, you must have seen. And these containers are lifted by hand or by electromagnet. What they do? So they use giant electromagnet in which they send the current and it becomes a really powerful magnet. So what you apply is a small field, but what it becomes is very powerful field because it's a ferromagnetic substance. So we generally use iron. So we use this is called electromagnet. So you by creating, by sending current, you become, you create a powerful electromagnet which you can stick the container. You will move to the destination and you will try to drop it. So to drop it, what will do? You will stop the current, isn't it?
Yes.
But if it is having very high retentivity, will it drop?
No.
So that's the bad thing, right? So to drop it, what will do? You will coerce. You will coerce by reversing the current, right? And then eventually it will drop because as the field will become weaker, it will drop eventually because of the gravity weight. Understood? So if we are trying to create an electromagnet, what property we should look for? High retentivity, high coercivity, low, low, high, low, low, high.
Low retentivity and high
High,
coercivity.
low, low, high, low, low, high, and it is all about RC, RC, RC,
Sir,
RC
both low.
is the right answer. Of course, we do not want high retentivity because that is also dangerous. And even if it is required to, make it zero, it should be less coercive, isn't it? So that we can make the domains go back to zero and we can drop the container. So they will ask a question that to create a electromagnet. So there are two types. Electromagnet means a temporary magnet and then permanent magnet. So for permanent magnet, what you want? Tell me.
High retentivity and high coercivity, sir.
Correct. So for electromagnet, which is like a temporary magnet, we want both to be low, but for permanent magnet, once we create the this ability, it should not get destroyed. That's the purpose, no? That's why we are creating permanent magnet, right? Oh, what I'm writing? Magnetic, I'm writing. Okay, anyway. Magnet. So for permanent magnet, what you want? The retentivity should also be high as well as coercivity, isn't it? Tell me, guys, is this clear? Hello,
Yes.
hello. Now you have two types of iron: soft versus soft iron versus steel. How you create a steel? So steel will have iron plus To harden it, we add carbon, right? And soft means pure, without carbon, right? No carbon. So tell me, in which case the domains can easily move right, left, up, down? When you put carbon, or when you don't put
Time.
carbon?
Soft.
Soft time.
Soft. So soft should be used for which one? The temporary or for permanent?
The temporary
Temporary.
ones.
Exactly. So soft iron we use for the temporary because it's easy to, it will have lower retentivity and a lower coercivity because the voids are present and which will allow the dipoles to rotate. But when you add carbon, carbon is a small in size, right? And this carbon will actually occupy the void spaces and therefore it will make it hard. Hard means you kind of restrict the lattice movement. Okay. And that is how you harden the substance. So steel is the hard iron and the pure steel is, pure iron is the soft iron by nature. So if someone will ask you to create permanent magnet, what we should use? Steel or soft iron? What you can say? For permanent, what you will use? Use?
Steel.
You will use steel, right? And area
Yes.
under the IH graph gives what? Energy density, energy loss per unit volume, right? So I'll just put this as a theory. There are two graphs. One is called BH graph. B means the net field. So if you draw the BH graph, it will also have the similar similar graph. You can draw 1, 2. 1, 2. So BH gives you energy, total energy, the total energy lost. Okay. Not per unit volume. But when you draw IS, the I by definition is per unit volume. So that's why it gives you the loss per unit volume of medium. So that's two things. If you remember, hopefully that will help you in solving. So bigger the area under BH graph, this area gives total heat loss per cycle of magnetization, demagnetization, area under IH graph gives what it gives? Energy loss or heat loss per unit volume. Heat loss per unit volume per cycle of magnetization demagnetization. And this is how we can end the chapter without worrying much. Okay. So now time has come for solving PYQs. Just a moment, let me share. Just let me see it. So you all can, open your PDF if you have. You all have, I hope so. Can someone check and tell me, I mean, it is on which page? Is it below? No, it should be below only. Hmm. No, I think it started. Let me check the topic.
Sir, it's on 340.
340. Okay. 340. Electrostatic. Magnetism and matter. Okay. 340. Let's go to 340. 340. Yes. How many questions? Oh, less only 40, 50 questions. That's it. Okay, let's start. 29 question you can see. So what is B? Make the correspondence of these bars with their material being dia, ferro, and para. So A is what?
Ferromagnetic.
I mean, it's very easy. And B is dia.
Dia.
So A ferro, B dia. Option B. Done. Okay, look at the 24th question quickly. The BH curve for a ferromagnetic is shown in figure. The ferromagnetic is placed inside a long solenoid with 1,000 turns per centimeter. The current that should be passed in the solenoid to demagnetize the ferromagnetic completely is. What is the HC? Can you see the HC value? The coercivity is how much? Can you see? On the x-axis?
100.
100. So by definition, 100 equals to Ni.
Yeah.
So 100 is given. N is number of turns per meter. 1,000 into 100, right?
Yes.
Into I. I hope you remember this. No one
Yes.
remembers this. So I is 1
Milliamp.
B option, correct? How to read it? Are you guys getting how to read these questions?
Yes, sir.
Is this clear, no? Doubt? Anyone having doubt?
No.
Because we for solenoid you have to remember the answer. H is always Ni, right? We have done this. Okay, next is 24th question. Read, everyone. The hysteresis loop for two magnetic metals A and B are given below. Okay. I think both are B and H only. So these materials are used to make magnets for electric generators, transformer core, and electromagnet core. Okay. So electric generators. In generator, what we use? Permanent or temporary?
Temporary.
No. Generators means, I know, it will have the fixed magnet.
As a horizontal field that we use for AC current.
Yeah. I mean, if you have a generator, it means you have to have the permanent field when you rotate the, so when you send the current in the coil, it will start rotating, right?
Yes.
So, okay, you need to know this. So electric generators, we need permanent magnet. But for transformer core will always use
Temporary,
AC,
sir.
AC, na? So
Yes, sir.
it will be get magnetized and demagnetized very often. So what kind of material is suitable to have better efficiency?
Sir,
Soft.
less energy loss.
Yeah, so it is must be soft, right?
Yes, sir.
So can you answer the question? So the
Sir,
graph,
is it B?
yeah. So B for
Bombay.
electromagnets. Yeah, that's correct. So B is for electromagnets and transformers. That's correct. And A is for the electric generators, but transformer is wrong. So that's why C is wrong. A for, okay, that's A for transform. That's wrong. So the correct answer is, guys, 24. Which answer is correct? B. B for electromagnets and transformer, because both will use temporary magnet, right? Hello, hello.
Yes.
Hello. I mean, you will magnetize temporary, right? You cannot keep it permanent. So in transformer, we don't use magnet, we use magnetic substance. We use iron core. Okay, anyway. So you can check the answer, it must be B only. Let's go to some unique problem, just a moment. So this you solve. Yeah. Read the question number 27. See, you will get most of the question of solenoid only. So if you know the formula of solenoid, you can answer it. So can you solve the 27th? And the benefit of this chapter is if you know the formula, you can answer it. That's it. So a certain, I mean, you can save your time in 30 seconds, 40 seconds, or maximum 1 minute, you can solve these questions with full marks.
Sir, 27th is C.
You can check, I haven't solved. Thus, can you,
Yeah, sir. I'm
Confirm?
also getting C.
yeah, that should be C only. You can just check the answer.
Yes,
Just
sir. Having C only.
okay, so you only check the answer. Didn't solve, huh? Did you solve? There? No.
Yes, sir, I solved that.
Okay, okay, fine. 20. Which question is this? 26, no? 26. Yeah, let's solve the Earth. This is Earth. 26 question. Can you read the question? I have to show it above also. If you have your PDF, you can read and tell me the answer. I think there is something magnetic meridian. I can read something to do with the Earth magnetism. That's why I'm trying to solve. Solve it and let me know. Then I'll attempt. See, north south you can take as the direction of magnetic field, right? BH. Ah, I got it. This is a tan B position, if you remember. See, when you say that you are drawing a line from the middle point of magnet, it is basically the perpendicular bisector, right?
Yeah.
Yes, sir.
And you know the formula for the perpendicular bisector, and that should be equal to BH. For the neutral point, they must cancel out each other.
Yes, sir.
Okay, try this. I mean, I will solve. It's easy. I know. But anyway, that will not click at first go. I mean, I know because you haven't practiced in past. So that will not click very easily. If it clicks, it's very easy. So neutral point means what? The two fields are cancelling out each other. That's it. Okay. Anyone getting the answer, please? You're just supposed to equate the two formula. Because they're asking the magnetic moment. I know the answer. The magnetic moment formula. Do you know? Dipole moment, na? So here the magnetic moment is basically magnetic dipole moment, right?
Sir, BH value is given.
Yeah, you can read up. Just a moment, I need to show you. It's 26. It is given, I think, here. Oh my God. Yeah, okay. It is here, the topmost.
Okay, sir. Thank you, sir.
3.6, 10⁻⁵. Which option there's?
Doing it one second.
I mean, just use the formula. Na? On equatorial portion, what is the B formula?
Minus KP by RQ.
No, there is not minus formula. Formula is simply mu naught by 4 pi m by RQ. That's it.
EM by RQ.
And that should be equals to BH.
3.6 into 10⁻⁵.
Yeah. And mu naught by 4 pi is 10⁻⁷. Substitute. M by RQ, R is given 30 centimeter. Convert. Please do this. Oh, but before you do this, you should realize this, why we are doing this.
Yes, sir.
So C option.
9.7.
9.7. Yeah, I mean, if you all are getting same answer, it should be same. Okay. You can check. Gar will check. Tell me. I think 27 is similar to what we have solved, right? Something similar. The coercivity is given.
Sir, we just
So we
solved
did
that.
27.
Yeah, 27 we have solved, no? This is I mean, something like this we have solved. I think. Let me see something new. I mean, some fresh question. See, they have the similar question again. So this question is important. The coercivity is important. I can see this. Okay. So 15 and 21. I think that is something fresh. 15 and 21. So first you solve 15 and then 16, I mean, then 21 and then anything else. I can see one thing. The coercivity question is very famous in solenoid, right? They're so much happy about asking the same question every year. Good. Which means you know that which question you are supposed to practice more. And see, you have only 50, 60 questions to practice. I mean, less than 50, I think. And that will give you minimum 1 to 2 questions. So I think we are done with all small chapters, right? Or any chapter left? All the
Sir,
JEE.
thermo we have to complete.
Yeah, thermo. Okay, thermo will continue now. Now, see, there is no other chapter left. So we are going to only focus on thermo now. Okay.
Sir, AC wave you told you completed.
AC you have to study from, read from the like video.
Recording.
Yeah, recording.
Okay.
So I might teach if the time is left, but I don't think that we will have enough time now. And I think that you guys should revise for the last week instead of studying new chapter. Rather, whatever we have covered, if you just try to cover those things, revise, rewind, try to remember every formula, write a formula on wall, on paper, hand, in everywhere else, on your body, in the mirror, everywhere. So wherever you find space, just write all the formula. Keep on writing the formula day in, day out. Become mad for 1 week, and then your examination will be really good. So don't rely on the fact that your brain will give you the recall of the formula. In examination, what will happen? You know the process, but you will forget the formula. So you have to keep on revising the formula from all chapters. So keep on, revisiting the terms, topic. Just see the notes, keep on seeing the notes, write the formula. If you don't remember, write it down everywhere. So keep on writing, just randomly. In 1 week, you need to just kind of recall every formula at least from physics. Then only you can get a good score. Good means very good score. Anyone got the date for the examination? Exact? No one.
Not yet, sir. Sir, it will be
No.
out 15th, I think.
24th onwards, not 21. It's a 21st or 24th.
No, 24th to 31st. But sir, still the registration is only going on.
Well, today is the last day for the registration, so I think
Okay. Yeah. Then you will get the deadline. I mean, maybe in the next, I think before the next week only. I mean, Monday before only. Okay. Anyway. So now don't try to study new chapter. First, you try to finish what you have covered. And once that part is done, revision is done, you have written all the formula, then try to, with the remaining time, try to add chapters as you go forward. Okay. So don't keep on running forward and forgetting everything. Rather try to recall. So are you guys writing all the formula from all chapters? No.
Sometimes, sir.
So do you remember all formula?
Sir, mostly, sir. The main formulas and all I remember.
Very good. Now, if you remember, it's really good. If you not, I mean, because see, these chapters are you're studying for the first time, it's a unique chapter. So you have to keep on watching the formula of semiconductor communication, EM wave, and this magnetism chapter. And then one more small chapter was which one? What do we cover? Modern physics also. Yes. I mean, all this extra lecture which we have covered. Let me just see. Search. Yeah, got it. So first is modern physics, which you should write down all formulas from all topics, subtopics, and make sure that you remember everything. Semiconductor, give at least 2 revision before the examination. EM wave, it's easy. If you remember the formula, you can answer. Error analysis, the vernier caliper and this which problem you do. Don't try to read the theory. Just try to solve numerical and from there try to retain the formula. Okay. And communication, keep on revising the formula at least. Okay. Then earth, then this entire magnetism part. Again, keep on doing the same. So tomorrow is what? Tomorrow is Thursday, right?
Yes, sir.
So tomorrow class will start at 6 o'clock for thermodynamics. And hopefully we are going to finish the entire chapter tomorrow itself. Till whatever time. I'll give you breaks from 6 to 9. Then 9 to 10 will be break. And then from 10 onwards. Okay.
Okay, sir.
I hope you will have energy to complete with me. Okay. So that way we are going to finish the thermodynamics part yesterday and tomorrow it's itself. Okay. And then with remaining time, I will say that okay, don't try to learn something new, rather try to revise. That will give you more marks for sure. Okay. All right. Done. 15 done. A paramagnetic sample shows a net magnetization of 6 ampere per meter when it is placed in an external magnetic field of 0.4 Tesla at a temperature of 4 Kelvin. When the sample is placed in an external magnetic field of 0.3 Tesla at a temperature of 24 Kelvin, then the magnetization will be. Yeah. Do we need to find the temperature relation? The susceptibility. Okay. So susceptibility is inversely proportional to temperature, right? So that we might have to use. Okay. That seems interesting. Let me resolve this first. So I have even seen for the first time. Okay. So a paramagnetic sample shows a magnetization of net magnetization of 6 ampere per meter. So 6 ampere per meter means what? What is given to you? I is given to you, right?
Yes.
And when it is placed in an external magnetic field of 0.4 Tesla. So external field is given 0.4 Tesla. So we have the H equals to B by mu naught minus I. But B is given the external field. It is not the net field.
Net field.
It is the external field. Okay, okay. So we can add simply B by I because I is not coming. It is not there. Okay, okay. So let me remove this part. So B E external upon mu naught. That's fine. Okay. And then I equals to H equals to I by X. So you can say I equals to what is happening? Susceptibility into H. Okay, fine. And susceptibility is C by T, right? Okay. So do we need to do something here? So as temperature will increase, the susceptibility will I got it.
Decrease.
Yeah. So we can say that so the susceptibility of what is happening? Just a minute. It is hanging a lot. Just a minute. Yeah. So susceptibility at first case is C by 4 and the case 2 is how much? C by 24, right? So we have to use this relation and then intensity is how much? X times H, right? So I1 is X1 into H. So I2 is how much, guys? X2 into H2, isn't it? So I2 by I1 will be how much? X2 by X1, H2 by H1, because H is given differently, right? So now we can substitute the answer. X2 by X1 is how much, guys? X2 by X1 is 1 by 4, 1 by 6, right?
Yes, sir.
1/6. And H2 by H1 is same as B2 by B1 because mu naught is common, right? So 0.3 by 0.4, right? Tell me guys, can we write like this?
Yes, sir.
I2 is how much? 1/6 into 3/4 into 6, right? So 3/4 is how much? 0.75. Nice. This is challenging problem. You can keep this. Check the answer, anyone? 0.75 is the answer. Okay, temperature
Yes,
gave
sir.
us the hint that it has to do with the susceptibility, and external field we can always write as H equals to B external, like the applied one upon mu naught. Mu naught will get cancelled, so we can use this relation directly. Okay, so this is done. Can you do this 21? Solve 21. So the needle length is given, pole is strength is given, which means you can find the dipole moment, isn't it?
Yes, sir.
And 10 and 45 means what? The B.
BV equal to BH.
Yeah, so B cos 45 is BH, right? You can find the net B, right?
Yes, sir.
Okay, so that's fine. You can solve, I think.
Sir, net PV are just balancing out the BV components, sir.
Yeah, we have to apply
We just
the
need the
field
vertical, right?
Yeah, we just need to balance the vertical, and we know the vertical and horizontal are equal because 45 degrees, no?
Yes.
Yes, sir.
So I think that's it. So vertical force that should be applied to one of its end. So force is how much? You have to find. Okay, they're asking the force actually.
We have to balance the torque here.
Yeah, so balance the torque about the center, that's it. So make it horizontal and write the force at one end. F into L by 2. Understood? Equals to the magnetic torque. Which is couple force, right?
Couple torque. Yeah.
Yeah. So it is MBH into L. I can see. If you remember that way of writing,
Yes.
so answer is 2 MBH.
So L isn't actually needed.
Yeah, L is given, but it's not required. L is given, no? L is given. So 2M, pole distance is given.
Yes.
1.8. And BH is 18 into 10 power minus 6. How much is that? 18 square. 18 square is how much? 324. How much is 18 square? 324, no?
Sir,
Yeah.
yes, sir.
324 into 2. 648.
6.5.
So 6.5 10 power minus 5. Then D option is close answer. Can you check?
Yes, sir. That's correct.
So it is simple. No? You have to think as north, south. You want to keep it this way, right? So the BH will act in which direction? I think BH not BV will act like this. MBV. MBV, because both are same, right? And you're supposed to apply force here, right? To keep it horizontal. I mean opposite like this. So the torque about the center is how much? F into L by 2. And torque of couple force is how much? MBH into L, right? MBV into L, but BV, BH are same, so we can get the answer. I hope this is clear. So it is question of like, I mean, rotational dynamics, the torque question. Tell me, Darsh, Hasika, is this clear? Hello,
Yes,
hello, hello. Okay, so we can
Yes,
do
sir.
next question. So you want more question or you can practice at home? What do you want? So this is one part. I think this is easy one. Yes. Question number 12, a diet formula, if you remember.
yes, sir.
It's energy and all and all and all. And question 9 we have done in already in the class. A thin circular disk of radius r is uniformly charged with sigma. The disk rotates about its axis with uniform angular velocity omega. The magnetic moment of disk is. Do you remember this answer? Pm by L equals to Q by 2m. Anyway, don't remember this. 9th question, can you see?
Yes.
I mean, this is from the regular magnetism. Then this is the axial and equatorial position for both the magnet. Find the net field and do it vector summation. You'll get the answer. Question 3rd I'm talking about. Okay. That's it. This is current sensitivity of, okay, this is which chapter? Current or magnetism. Okay, they have taught in this in magnetism, yes. So I hope you can do this question. Okay, they have given solution also. That's, you can see if you want. But mostly you should be able to do this without any difficulty. The 40 is bonus. See, the 40 question we have done, right? Something like this. The time period and B relation. The oscillation magnetometer, right?
Yes,
This
sir.
is oscillation magnetometer. This is again oscillation magnetometer. So there are many questions from oscillation. Electromagnetic induction. Okay, anything. All right, guys. So let's stop it.